Great.
Welcome everyone to this uranium isotope proxy primer. As Kim was mentioning, it's about 1 a.m. here in Brisbane, and it's just rolled into my birthday actually, but I'm getting to start this day with the best possible way, which is learning geochemistry from a world's expert. So most of the people here are familiar with SGP, but for those of you who aren't, we're an open community-oriented research consortium seeking to address questions of environmental evolution across Earth history through statistical analyses of the sedimentary geochemical record. Our database, and we're looking forward to a phase 2 data release in February or March of this upcoming year, has currently about 113,000 samples and coming up on 4 million analytical results. This has been built by greater than 170 collaborators around the world. And if you're not part of SGP, we would really love you to join. Get in touch with us. We started this SGP Proxy Primer series to have a space where some of the world experts can accessibly explain the basics of a geochemical or proxy method to a broad audience of geologists, geochemists, and paleontologists. The other point here was to be able to curate lecture videos on our SGP YouTube channel to create a proxy video library for people to look at. And then afterwards, provide an informal space for interaction with experts on each proxy. This year, we have 4 online events. Our first is our Proxy Primer with Dr. Kim Lau. Coming up in June, we have a Proxy Primer with Tianron Zhang from Dartmouth, and Martin Smith and Killian Eikens here at Durham, looking at Bayesian approaches in stratigraphy. Then we'll have a break for the North American summer field season. And come back in October for an update call where we'll go over the phase 2 database, working group updates from various groups, and changes to our website. And then finally, in November, we'll have one on strontium isotopes from Graham Shields and Ying Zhu at University College London. So with that, I will turn it over to Kim. Dr. Lau did her undergraduate degree at Yale University before coming to my institution, Stanford, for her PhD, and then going on to University of California, Riverside for her postdoc. She spent a stint at the University of Wyoming as an assistant professor, and then moved on to Penn State, where she is now. And I'm looking forward to learning about uranium isotopes.
Thanks, Eric. All right, let me get set up. Let's see, okay, does this look right?
Yep.
All right. Great. So thanks, everyone. I'm really excited to give a proxy primer on uranium isotope as a pillar redox proxy. Uranium cycle is really interesting. Uranium is a trace element in almost all rocks, and yet it plays a really important role in many different geological tools that we use, from, of course, uranium geochronology all the way to these redox proxies I'll be talking about today. And my goal for this talk is to provide an overview, but as you'll see in a few slides, there's been so many recent papers. I also want to be sure to include at least mentions of some of the recent work, so that if you're interested, you can read some of these papers and be acquainted with some of the new ideas coming out about this proxy, how to interpret it, and how to, what does it actually mean? Okay, so just some basics. Uranium isotopes are reported delta notation using typical delta notation nomenclature, including the per mil unit. It's normalized generally to CRM 145, which is a solution, or CRM 112A, which is a solid of the same material. It's considered to be a natural standard with ratio of 137.844, 238-235 uranium. Both uranium-238 and 235 are radiogenic, but they have very long half-lives. And so they're often called stable, even though technically they are radiogenic. An important note is that the 238-235 ratio of a given sample does evolve through time through radioactive decay.
Because the word extreme here is referred to life. We know, or we believe we know the limits of life on our planet. They are not.
Okay. But the delta value does not change through time, and that's because the 238-235 ratio
levels and so on.
of the standard is also evolve through time through radiogenic decay. So the delta value should be constant of a given sample. All right, as I was mentioning, there's been this huge increase in uranium isotope papers due to analytical advancements. So this is a really neat compilation from Lee and Tissot 2022 that I'll be talking about at the end of the talk, where they're showing the number of publications per year using uranium isotopes 238, 235 in any geologic material. And you can see that with the rise in multi-collector ICP-MS, we're able to now collect these data with enough precision to make useful interpretations and relatively easily. And so what I'll be talking about in this talk is really some of the new findings that you can see in these last 10 to 15 years and this exponential rise. Very briefly, in terms of analyses, a double spike is commonly used. It's a 233, 236 double spike that's present in about a 1-to-1 ratio. There's different leach procedures depending on your sample type. Carbonate dissolution is typically a moderate acid leach, weak to moderate acid leach to try to target just the carbonate phase. And this was summarized very nicely in 2 papers, Clarkson et al. In 2020, as well as Fei Zhang's review in 2020 as well. And so I encourage you to look at that, as the carbonate dissolution procedure does vary depending on which lab group. But I think the main takeaway is that there does not seem to be a major impact of the carbonate leach procedure on the delta 238 uranium value. For siliciclastic rocks, typically a whole rock dissolution procedure is employed. Uranium separation can use a multiple range of different resins. Butiva and True are the most common ones. And usually a multi-separation step is used to separate uranium multiple times from calcium, sodium, and other components of the rock. And as I'm showing here, nearly all the analyses, at least for the redox proxy, are conducted using multi-collector ICP-MS. All right, so some basics about uranium geochemistry before I dive into the specifics of this proxy. The foundation of the proxy is that uranium occurs primarily in 2 redox states, uranium 6+ and uranium 4+. And these 2 valence states have very different geochemical behaviors. Uranium 6+ is soluble and is readily present in aqueous forms, whereas the reduced form, uranium 4+, is particle reactive and is generally considered to be insoluble. And so as you can see in these 2 compilations of uranium concentrations in carbonates in the upper right and in shales, there's been a change in uranium concentrations in the last 3.5 billion years that has been thought to track the size of the uranium reservoir and whether it is present in this soluble uranium 6 oxidized form or the reduced insoluble uranium 4. And as a result, the modern residence time of uranium is about 400,000 years. And so very generally, what this means is that as atmospheric oxygen has gone up, then we expect dissolved oxygen in the oceans to also go up. And because of this, we also see more uranium-4 oxidative weathering and a higher reservoir of uranium-6 in seawater. At the same time, with higher dissolved oxygen, we also see lower uranium-4 burial in the ocean, which I'll talk about in a few slides. And the same effect is that there's an increase in uranium-6 concentrations through time. So this is the effect on the uranium concentrations in seawater, which is inferred from uranium concentrations in carbonates and siliciclastic rocks. In terms of the isotopes, there's also a different behavior between 238 and 235. Those are the 2 most abundant isotopes of uranium that can be measured with confidence on multi-collector ICP-MS. And the premise of this is that 238 uranium is preferentially partitioned to uranium 4+, and this is through a mass-independent isotope fractionation that is dependent more on the volume of the isotopes rather than the mass. And that's just because uranium is so heavy that the difference in mass is actually not as important as the difference in volume as you add those 2 extra neutrons. The uranium redox proxy is interesting in that the uranium redox couple is tied to the iron redox couple here. And so on face value, it's thought to record changes in ferruginous conditions. And this is useful when comparing the uranium proxy with other redox proxies. As you can see, they have different sensitivities to different EH redox potentials. But this is most likely more complicated than this, as we can see in modern settings. The early studies of uranium isotopes were based on the fact that the delta-238 uranium value of sediments and rocks differ depending on the assumed oxidation state of that setting. So this is a compilation of uranium isotopes and different rocks and different components of the Earth system. So here's the delta-238 uranium value. Modern seawater is -0.4 per mil, and the average continental crust is about -0.3 per mil. Rivers generally track this upper continental crust value. I see now I've lost some of my y-axis, so I apologize here. This is dust. This is the Aeolian flux and assumed groundwater that are assumed to also track the continental crust. And in black here are euxinic sediments, and then blue are carbonates, and then in green are manganese and iron oxides, and in gray are basalt alteration estimates at low and high temperatures. And so the foundation is that there seems to be a difference in the delta-238 uranium value between sinks of uranium that are reducing, assumed to be uranium-4, such as these euxinic and hypoxic sediments, compared to uranium, delta-238 uranium values in sediments that are thought to be more oxic, that contain uranium-6, such as iron and manganese oxides, as well as primary carbonate. So there's this lever where you can see if you have more organic carbon or more uranium-4 burial, then we would expect that to have a major control on seawater delta-238 uranium. In terms of isotope fractionation, there has been some interesting studies that suggest that there might be a strong biological control in isotope fractionation, but it's also been observed that abiotic uranium reduction can also induce a large fractionation. And so it appears that generally uranium reduction is able to impart a large fractionation. The magnitude of fractionation can depend on the reduction rate, which is pretty interesting as a way of thinking about what might be driving uranium fractionation changes through time. So it's a very simplified cartoon of how these can all tie together. The way we can think about this is most uranium enters the ocean through rivers as the form of uranium-6 today. And so in oxygen ocean, there's high concentration of uranium and it's present as uranium-6. And those uranium species can be removed in two major sinks, the oxic sink, which can remove primarily uranium-6. So this can be, for example, carbonates, as well as manganese and iron oxides. And then in reducing sinks, we assume that they're removing uranium-4+. And so what we can see is that as the reducing sinks increase, we see more reduction of uranium and transformation of uranium-6 to uranium-4+. And that will result in two different effects. One is you have a decrease in the concentration of uranium with greater anoxia and greater reducing seafloor. And because you have more sequestration of uranium-238 compared to uranium-235, we also expect the delta-238 uranium value of the seawater to go down. And so we potentially have two different sinks to look at in terms of tracking uranium isotopes through time. We can track either the oxic sediments, which we can assume will passively track the delta-238 uranium value of seawater, or we can track the reducing sediments themselves, which can tell us not only changes in seawater, but perhaps the degree of fractionation associated with that environment. So I've been mentioning the sediments, and that's because early studies indicate that uranium reduction primarily occurs on the seafloor. And this has been an interesting perhaps a distinction of uranium isotopes compared to other redox proxy in that there's a strong seafloor control on the seawater concentrations. And so generally what this means is that uranium-6 diffuses into sediments. This is the sediment-water interface, and it can get reduced from uranium-6 to uranium-4 in the sediments. And why this is important is that what we see is that there's an intrinsic fractionation, isotope fractionation associated with the reduction of uranium-6 to uranium-4. And so that's depicted here if you have uranium reduction in the water column as well as in the sediments. But because there is diffusion limitation of uranium from the seawater into the pore water, what that means is that there's an effective isotope fractionation that's actually preserved in sediments that is not the same magnitude as the intrinsic isotope fractionation. And in fact, it's almost always, it's always smaller, anywhere from 0.5, half the intrinsic fractionation to perhaps the full amount, depending on the reduction and where that's taking place. And so there's been a range of modeling studies as well as studies of observations in modern settings that have looked and tried to quantify this effective diffusion limitation of uranium into the pore waters. Okay, so along this theme of different phases of uranium and what they can mean, there's been a lot of recent studies that have tried to characterize uranium and its valence states and its isotopic fractionation in different components. And so in the simplest conceptual model of uranium proxies, the assumption is that uranium-6 gets reduced to uranium-4, and that uranium-4 then gets incorporated into some mineral phase such as uraninite. And so this is pyrite, not uraninite, but this is the simplest interpretation of the proxy, is that when we have this sequestration of uranium-4 into a reduced mineral within the sediments, there's a fractionation that can range from 0.6 per mil to 1 per mil, and it's primarily uranium-4. There's been some recent studies looking at organic matter and how that can impact uranium isotope fractionation as well. And this is really interesting because we can see a whole range of isotope values associated with this potential sink. And it depends on whether or not whether uranium is being incorporated as uranium-4 into organic matter or absorbing uranium-6. And so this can, if uranium-6 is absorbing onto organic matter, it will be a negative fractionation of about -1 per mil onto, for example, some studies of plankton. Uranium-4 into organic matter, however, on organic floccules is thought to have a large positive fractionation of about 1 per mil. I'll discuss this in much greater detail later on, but there's some characterization of uranium valence states in different authigenic minerals, such as calcium carbonate, as well as apatite. And in this case, we assume that there's a combination of U6 and U4 that can be incorporated into these authigenic minerals. And the fractionation also varies, and it's partly a reflection of diagenesis and how this can reflect the diagenic process. But there's also a range in isotope fractionations associated with zinc as well. And finally, this is sort of an interesting side story of uranium isotopes. There are also studies of uranium isotopes and how they are recorded in iron and manganese oxides through time. And the isotope fractionation in this case is pretty well constrained to be about -0.2 per mil, and it's thought to be primarily U6, but a recent study has found U5 in some mineralized hematite. Okay, so that just gives you a sense of the complexity of uranium and the different ways it can be removed into different geologic materials. If we view this from a uranium budget perspective, we can see that there is a wide variety of depositional settings that can have different isotopic fractionations and therefore different delta-230 uranium values. So I'm just going to highlight some key ones here. Again, the main input is thought to be rivers. This is thought to be about 90% of the total input. And the delta-230 uranium value tracks the upper continental crustus, which is roughly -0.3 per mil. And then we have a range of different sinks. So again, we have bulk carbonates, and then we have ferromanganese nodules. And then there's different types of reducing settings, euxinic sediments and hypoxic or ferruginous settings that might have different isotope fractionation values. And then I won't talk about this very much in this talk, but there's also basalt alteration that, depending on whether it's high temperature or low temperature, will have different isotope fractionations. But this is considered to be a relatively small output flux, and so it is not generally considered to be a main driver of seawater uranium isotopes through time. So today, uranium isotopes in seawater is about -0.39 per mil. This has been confirmed through various studies, and it's present at very low concentrations, roughly 13.4 nanomoles per kilogram, or 3.2 ppb. Okay, so I can simplify that uranium budget into a box model approach, and I'm just going to use this to ground us as we talk through different components of the uranium budget for the rest of this primer. So first, I'm going to talk about different uncertainties in these different components of the uranium isotope budget. And I'm going to talk about rivers first. This isn't really considered to be, there hasn't been too many constraints on how this could have changed through geologic time. But I think it's possible that it may have changed depending on the lithologies that are being weathered and the kind of weathering that's taking place. So these are some rough potential calculations of Delta-238 uranium of rivers that might have varied as a function of lithologic change of what's exposed on Earth's continents through time. This is from a compilation from Bluth and Kump. And so this is from 600 million years ago until today. These are two different calculations based on what we assume is the primary contribution of uranium to seawater. And this was done just to highlight that there could be a potential range in Delta-238 uraniums of rivers. Just to orient you, this arrow is pointing to the modern flux-weighted average of negative 0.34 per mil. And these calculations here are done assuming different carbonate Delta-238 uranium values and whether or not they change through time. But you can see that depending on the assumption, there could be a range of about 10.1 per mil in the riverine input. And then if we also make some calculations assuming different values of the Delta-238 uranium of exposed shales, we can also produce about 0.2 per mil difference in the Delta-238 uranium value of rivers. So I think it's possible, but it's difficult to confirm whether or not this might have changed through time. Okay, so I'll also next talk a little bit about uranium isotopes in ferromanganese crusts. Experiments and observations agree that there's a negative 0.2 per mil excursion or isotope fractionation during uranium absorption to iron and manganese oxides. And this has been used to then estimate how uranium isotopes of seawater have changed through time. So this is a nice compilation of uranium isotopes in manganese nodules from the Cenozoic. And this paper argued that because there wasn't very much change, that the Delta-238 uranium of seawater has stayed relatively invariant over the last 80 million years. And similarly, a record from iron-rich rocks was used to potentially track changes in seawater, Delta-238 uranium from 4 billion years ago until the present. And this, in combination with siliciclastics and carbonates, was interpreted to potentially track an increase in oxygenation in the Proterozoic. So there haven't been too many studies, but I did want to highlight these two as being really useful checkpoints as to how seawater could have changed and as a comparison to uranium isotopes and carbonates as well as to shales. And the assumption of this is that they're primarily uranium-4 that's deposited under oxide conditions, but I wanted to highlight an interesting study published just 2 years ago that did find uranium-5 in Proterozoic mineralized hematite from Australia. So unclear what the significance of that is and how prevalent that uranium-5 is in iron oxides and other iron oxides in the geologic record. Okay, so I'm next going to talk about uranium isotope records and isotope fractionation and what I'll group together as reducing settings. And I'm doing this because there's been a range of opinions and applications, whether in terms of whether uranium isotopes are interpreted to have different Delta-238 uranium values in euxinic versus hypoxic sediments and what this could mean. So this is a nice compilation of uranium isotopes that Xinming Chen put together and published in 2021. And this isn't, I haven't pulled out here shales versus carbonates, but I just wanted to highlight that there is a really robust Delta-238 uranium record, and a significant proportion of it do come from organic rich shales. Generally, in shale records, the Delta-238 uranium value is calculated using the uranium-aluminum ratio of those rocks to estimate the authigenic fraction. In other words, we try to separate out the detrital fraction from the authigenic fraction that we assume is recording seawater uranium cycling. In one of the early papers that looked at Delta-238 uranium of shales, found that in 2.5 billion-year-old Mount McRae shales, the Delta-238 uranium value was higher than continental crusts by about 0.1 per mil. And these authors interpreted this record to therefore indicate oxidative weathering of uranium and the increase of the uranium reservoir. So I wanted to highlight that as an important paper that developed this proxy. The challenge of uranium isotopes and in shales is that there is a very wide range of Delta-238 uranium values that have been observed in modern settings. So this is a recent compilation that just came out this year. This is a really nice depiction of this range that we can see. And you can see that the delta 238 uranium value in sediments, primarily plotted here, versus waters that fall here, do tend to be higher compared to seawater, modern seawater here, but that there is a huge range in values. Some of these might correspond to whether or not they are deposited in ferruginous lakes, ferruginous conditions versus euxinic conditions. So that might partially explain the difference here between these values and these values. There also are differences depending on whether the sediments are deposited in restricted basins, primarily these samples, compared to epicontinental upwelling regions, which are these blue samples here. So you can see it's difficult to disentangle what is driving this variability. Is it the redox setting? Is it the depositional setting, the tectonic setting of where sedimentation is occurring, or is it some other factor? Before I get into this, the potential differences in what's driving uranium isotope fractionation, I did want to talk a little bit about how uranium isotope fractionation in sediments can then impart changes to water column uranium. And this might not be very straightforward, but the way this can work is that essentially we create a diffusion, a concentration gradient in the sediment pore waters, and that can then in fact result in diffusion of seawaters, differential diffusion from seawater into sediments. And because of that, there could be different diffusion gradients between uranium-238 and 235, and that can then impart an isotope fractionation. Okay, so let me try to explain that in greater detail here. These are some model results of pore water profiles of 238 in the squares and 235 in the open symbols. And this is depth in the sediment column. Blue are modeled profiles in a strongly reducing, a very low oxygen setting, whereas purple is the modeled profile where there's higher amounts of oxygen that's present in the pore waters. So in this case, the uranium-235 has been multiplied by 100 for both the blue and the purple, just so that we can see them more easily on the same scale. But what I want to show you is that in both cases, there is a larger concentration gradient for 238 in the closed symbols than for 235 in the open symbols. So what this means is that there is greater reduction of uranium in the sediments. That means that you have more drawdown of 238 relative to 235. Because of that, there's a greater diffusion gradient for 238 uranium compared to 235 uranium. And as a result, you'll have more diffusion of 238 uranium from seawater into pore waters compared to 235. If there's sufficient uranium reduction in sediments, what this means is that the seawater 238-235 ratio can go down, which will result in lower delta 238 uranium of seawater because of greater reduction. And so this is the conceptual model of how sedimentary processes and sediment reduction can actually impact the seawater itself. Okay, so as I just showed you, there is a lot of observations that support variable uranium isotope fractionation in different reducing settings today in modern sediments. This has been observed as well in a compilation that I seem to have deleted on accident, so I apologize. But there's a strong relationship. Let me go back to that compilation here. Okay, so in addition to differences in uranium isotopes, we also see differences in uranium concentrations in these different settings that probably are linked together, and they demonstrate that there's different ways in which uranium is being sequestered from the sediment, from the pore fluid, sorry, from the water column into sediments. There's been a whole suite of different ideas that have been proposed that can explain this variable uranium isotope fractionation. On the left, I'm just showing some reactive transfer modeling that tried to simulate uranium diagenesis. And I just want to highlight this middle panel here. On the y-axis is uranium isotope fractionation that's observed in sediments. And then this is the inferred reduction rate of uranium in the sediments. And what this modeling demonstrates is that as you have greater amounts of uranium reduction, you're able to impart a smaller degree of uranium isotope fractionation as we get closer to complete isotope uranium reduction. So in other words, there's a there's a Rayleigh distillation effect that's being observed in sediments that can impact the observed uranium isotope fractionation. In addition to the potential for the reduction of uranium in sediments itself to impart changes in isotope fractionation, there are a lot of different factors in the depositional environment as well that have been proposed to impact uranium isotope fractionation. So here's a list of some recent papers. Organic carbon loading in the Peruvian OMZ has been observed to result in different uranium isotope values. Lateral transport of organics, which is observed in Namibia, can also result in reoxidation of uranium and impact the uranium isotope values of sediments. Absorption to plankton, and this is assumed to be uranium-6, can produce large negative isotope fractionations, and this has been observed both in experiments as well as in several modern settings. Conversely, large uranium incorporation to organic floccules at the sediment water interface, so not diagenetically, is observed to have a large positive isotope fractionation of about 1 per mil. So this is essentially equivalent to what we expect the microbial isotope fractionation to be. However, a lot of these modeling and observations and interpretations rely on assuming that we're reaching some sort of steady state in terms of uranium diagenesis. And then maybe even this last paper I'm highlighting here proposed that we're actually not seeing steady state conditions, that it's a very dynamic uranium cycling in sediments, and it's not always very easy to assume that there's a constant isotope fractionation in reducing settings. So in terms of whether or not we see evidence for variable uranium isotope fractionation in the rock record, I wanted to highlight two examples. This is a recent paper published this year from the Lower Mississippi and Sunburn Shale from the Appalachian Basin, where these authors looked at delta-230 uranium value in several coeval cores arrayed along a depth gradient and at different redox conditions. And what it's plotted here is iron speciation on the x-axis. Here's the highly reactive to total iron, and then the pyrite iron to highly reactive ratio compared to uranium isotopes on the y-axis. And I just wanted, the main takeaway is that there's a range of uranium isotopes and that there's no clear relationship between iron speciation and therefore Ferruginous versus Euxinic conditions and the uranium isotope value. Similarly, a study of uranium isotopes in the Miocene Monterey Formation in two different basins showed that there were stratigraphic changes in delta-238 uranium through time. So this is the Santa Barbara Basin, this is Naples Beach, and this is a drill core from the San Joaquin Basin. And the stratigraphic changes in uranium isotopes don't correlate between the sections and were interpreted to reflect changes in basin restriction as well as changes in productivity. And so I think this is evidence that there is variable uranium isotope fractionation in the rock record as well as in modern settings, and that when interpreting uranium isotopes through time, it's not necessarily straightforward to assume an invariant uranium isotope fractionation into reducing settings. And this is perhaps akin to sulfur isotopes. This is just highlighting that in the modern, there is no noticeable difference in uranium isotopes between carbonates in blue and organic rich sediments in gray. In fact, they overlap, which suggests a very different isotope fractionation compared to, let's say, OAE2, where there's a significant difference between the uranium isotopes in shales in gray versus uranium isotopes in carbonates in this blue. And so perhaps this is again indicating that the fractionation factor in reducing settings has changed through time. However, despite the complications, there are several methods to try to disentangle these local effects on uranium isotope fractionation if you were to interpret uranium isotopes in shales as a paleoredox proxy. And there's been some really nice examples of this, coupling uranium isotopes and molybdenum isotopes in the same samples. And so I just want to highlight a few of these that have done this successfully. And here, this is a cross plot of molybdenum isotopes versus uranium isotopes in the same samples here. And these authors argued that if there was a global control on these proxies, we would expect to see a positive covariation, but instead the fact that there's a negative covariation indicates that there are local factors that are in fact controlling especially these proxies, especially uranium isotopes. And so these coupled molybdenum and uranium isotopes have also been modeled as a way to infer euxinic seafloor changes through time. And so I apologize, I lost a few slides, but I just wanted to go back and highlight again. Sorry, let me scroll back a few slides here. I think there's still a lot of questions about how to interpret uranium isotopes. There's some evidence that their fractionation factor is highly reflective of sulfidic conditions. And so there might, compared to suboxic or lower or less reducing conditions. And so perhaps one of the ways we can interpret uranium isotopes through time is differences in the degree of euxinia compared to suboxic or anoxic conditions. However, I think there's also plenty of evidence that indicates that there's just large variability in general, and it's not necessarily as simple as thinking about euxinic versus ferrugenic conditions, but as thinking also about the style of uranium reduction, whether that's occurring in the water column, in the sediments, and whether or not the reduction in sediments is reflecting restricted uranium reduction versus highly productive anoxic conditions. Okay. I apologize again for losing those slides. So I want to also spend some time talking about uranium isotopes and carbonates and what we know and don't know about uranium isotope fractionation and the impact of diagenesis on this sink. The carbonate uranium isotope record has been really useful for tracking redox changes through time. It makes up a large component of the data that have been collected in this compilation that I'm showing here. But it is a bit of a scattershot record. So this is a nice summary from Fei-Fei Zhang's 2020 review of uranium isotopes through the last 600 million years. And there's been new data since. But what this is highlighting is that the carbonate uranium isotope record is rather sporadic. It's been collected primarily to target specific events, and we don't necessarily have a nice record that fills in these the baseline delta 230 uranium values through time. The modeling of uranium of global redox change is primarily using uranium isotopes is primarily based on carbonate delta 238 uranium. Some researchers will refer to this as carbonate associated uranium, and we'll add this subscript with CAU at the end of delta 238 uranium. So you might see that in a few papers. And generally the premise of this is that if we assume that uranium fractionation primarily is driven by reducing anoxic or euxinic sediments with the largest fractionation, then we can use the modern uranium cycle to calibrate the area of anoxic seafloor that this delta 238 uranium value is associated with. In other words, instead of simply reconstructing the change in this flux of reducing uranium through time, we can translate that to the area of anoxic seafloor that that's associated with. And two recent papers have improved on the earlier box modeling approaches by adding inverse modeling. So Kip and Tissot in 2022 and Pimentel-Galvin et al. In 2022 had two different approaches of trying to incorporate uncertainties that has sort of been the theme of this proxy primer into how we can then translate that to changes in global redox through time. I wanted to highlight a few other papers that have thought about using different isotope fractionations in ferruginous versus euxinic sediments to track the differences in ferruginous versus euxinic seafloor through time. So those papers are listed here. There's also been some efforts at thinking about this variability in uranium isotope fractionation and incorporating that in these box models themselves. So if you're interested in that, Qinming Chen's 2021 review has a nice discussion of that. And last, in terms of modeling, I wanted to highlight a 2021 paper that incorporated uranium isotopes as well as other local redox proxies into CGenie as a way of trying to use model data comparisons to try to understand changes in the carbon cycle and productivity during the Permian-Triassic mass extinction. Another modeling point I wanted to make is that a lot of the delta-238 uranium excursions that are observed in the Phanerozoic are often associated with negative carbon isotope excursions. And there's an interesting discussion here about the timing of negative carbon isotope excursions, as well as the onset of anoxia and what this could mean in terms of interpreting both the changes of carbon perturbations through time, as well as the timing of anoxia versus carbon cycle perturbations. And this was a really nice model study from Zhang et al. 2020 that discussed the timing of negative uranium isotope shifts versus the negative shifts that we observe in carbon isotopes. And so these are just different model runs that illustrate that depending on your model parameters, generally we expect carbon isotopes to decrease before uranium isotopes decrease. But this isn't necessarily what we see in many examples in the rock record. Okay, so as we dive into carbonate delta-238 uranium, the first question is, are carbonate uranium isotope records globally reproducible? Is this a record or archive that we can use to track redox changes through time? And I think the most promising example of this is from Permian-Triassic boundary sections. This is a compilation of 8 different sections in geographically disparate locations across the Paleotethys, as well as in the Panthalossoc Ocean, from several different studies. And in all of these sites, what we see is there's a negative delta-238 uranium excursion that's coincident with an increase in temperature and a negative carbon isotope excursion that's associated with volcanism at the Permo-Triassic boundary. And so this is, I think, good support for the idea that uranium isotopes can be reproducible, despite the fact that these are really different sites with different diagenetic histories. And importantly, this interpretation of more anoxia that we can infer from these uranium isotope records is in agreement with many other different redox proxies that indicate seafloor anoxia increased in the early Triassic. However, I will say that the estimates of the area of anoxic seafloor, or FANOX, do vary depending on the model parameters and the assumptions that you put into the model. And so the estimates range anywhere from 10% of the seafloor in the early Triassic to 20% of the seafloor in the early Triassic. And this is compared to about 0.6 to 0.7 per mole of the seafloor being anoxic today. So in both cases, these represent significant increases in seafloor anoxia. In comparison, the Cretaceous OAE2 has also been a time interval of study, and there's perhaps less agreement that I think is illustrative of uranium behavior in different kinds of carbonates. So not shown here are black shale records of uranium isotopes, and this was actually one of the first uranium isotope records in the geologic from Geologic Archive. So it's one that I wanted to highlight from Montoya Pino et al. 2010. And that study showed a negative shift of 0.15 per mil in one drill core from the mid-Atlantic. Several other carbonate sections have also recorded a negative delta-238 uranium excursion. And I want to highlight a few of them here. This is from Clarkson et al. 2018, where this is from Eastbourne, which is a pelagic carbonate section that was deposited in a Empiric Sea. And then on the bottom here is a record from the Portland core in the Western Interior Seaway, also pelagic carbonate section, also in an Empiric Sea. And they actually observed delta-238 uranium values that were much more negative, about -1 per mil more negative compared to what a -1 per mil excursion. This recent paper measured delta-238 uranium values in an open margin platform setting in Mexico, and they also observed a negative delta-238 uranium excursion in their carbonates as well. However, there is a lot of variability here. So the difference is anywhere from a -0.3 per mil excursion to -0.5 per mil excursion in this middle panel to a -0.9 excursion in this Western Interior Seaway section. In Clarkson et al., 2 other sections that were analyzed showed no negative excursion. And so the range of outcomes here may be representative of the effects of diagenesis and dolomitization, as well as the fact that perhaps uranium cycling might have been very different in empiric seas compared to open margin settings. So the takeaway here is I think that carbonate uranium isotopes do hold promise, but that they're similar to shales. There are different mechanisms that can result in delta 238 uranium values that don't straightforwardly record changes in seawater delta 238 uranium. Okay, so those are some examples from the geologic record. In terms of experiments, there have been a lot of work that has tried to constrain the isotope fractionation into carbonates. In primary calcite and aragonite, there's very minimal fractionation. This is a nice compilation that demonstrates the delta 238 uranium value in a suite of different corals, other aragonitic carbonates, as well as calcitic primary biocalcifiers. And there's a range of values, but in general, they all track seawater very nicely. And this is also observed not only in biogenic carbonates, but also in precipitation experiments in the lab as well. That there is a very minor difference between aragonite calcite that's generally within error of most measurements that can be done in most laboratories. There might be a small difference of up to 0.1 per mil as a result of carbonate speciation that might reflect a potential effect of pH through time. And so this has been done experimentally in this third bullet. And I also want to highlight the effect of dolomitization on uranium isotopes. Here, there's dolomite in gray and in red. And in general, there's no clear difference in dolomite versus limestone in terms of delta 238 uranium value. And so there's no, I think, clear evidence for isotope fractionation during dolomitization that is inherently different. However, as I'll get to in a few slides, this assumes that there is no specific change in oxidation state or redox or uranium reduction that occurs with dolomitization. This compilation shows really nicely, however, that there is a large difference between primary carbonates. So these are biogenic carbonates here, compared to most bulk sediments, where bulk sediments tend to be have higher delta 238 uranium values. And so two nice studies characterize the delta 238 uranium value of bulk carbonates from drill cores in the Bahamas. And that's what I'm highlighting here. This is from Chen et al., and this is from Francois Tissot and co-authors, both published in 2018. In both cases, this vertical blue line is the seawater delta 238 uranium or the inferred seawater delta 238 uranium value through time. And here, what we can see is in primary carbonates, there's no offset from seawater. But as we look at syndepositional or early diagenic carbonates to later alteration of carbonates, there is a significant positive offset of about negative 0.2526 to negative positive 0.26 per mil. And this is also shown in these drill cores here that are located in slightly deeper water environments, where we also see this positive offset of about negative 0.27 per mil relative to the primary delta 238 uranium value of seawater. In addition, we also see uranium enrichment. We see higher concentrations in general of the bulk carbonates compared to what we expect the primary concentrations of uranium should be. And so what's likely happening here is that during diagenesis, there is incorporation of reduced uranium-4, which has a higher delta 238 uranium value into the carbonate, and that will increase the uranium concentration of the bulk sediment, as well as increase the delta 238 uranium value. And so this is a nice conceptualization of these different effects. There could be mixing of different components. That's what's shown here, of pelagic, primarily calcitic carbonates versus more aragonitic carbonates here. But we also see this addition of your reduced uranium-4 primarily, which is assumed to then push the uranium concentrations to higher concentrations, as well as increase the delta 238 uranium value of these bulk carbonates. A paper published last year did a really nice separation of uranium-4 to try to quantify this addition of uranium-4 in bulk carbonates. These are samples from a drill core from the South China Sea. And what I'm showing here is on the x-axis, the percentage of U4 that is measured in the samples, and the y-axis is uranium concentration, and then the delta 238 uranium value here. And so what we can see is that as we increase the incorporation of U4 through diagenesis, we see an increase in the concentration. There's higher concentrations here. And we see a really clear increase in the delta-230 uranium value of those carbonates. And so I think this is strong support of this diagenetic factor where uranium reduction is occurring even in carbonate sediment settings that can then increase the delta-230 uranium value of carbonates and result in this offset. Using some simple diagenetic models, we can propose that this effect can have a noticeable effect on the delta-230 uranium value of carbonates. But if sediment buffered conditions are dominant, meaning that there is relatively low water rock concentrations, or there is sufficient time for the pore water geochemistry to reflect the sediment geochemistry, then even if the fluid is reducing, even if there's reduction taking place, there might be relatively limited alteration for carbonate delta-230 uranium. And so this is the case whether or not we're looking at meteoric fluids, that's in brown, versus reducing fluids in red, versus oxidizing diagenetic fluids in blue. So in other words, there could be a positive offset, and this will be particularly pronounced under fluid buffered conditions, but under sediment buffered conditions, this might be relatively limited effect. Okay, so I just want to use the last couple of minutes to place the uranium isotope proxy in context with other redox proxies. I showed this earlier, just highlighting, I think the theme of this proxy primer is what can we learn from different proxies and how can we perhaps interpret them in conjunction with each other. As I mentioned, uranium isotopes reflect ferruginous conditions because uranium reduction occurs roughly where the iron redox potential is expected to take place, but there's a strong effect of sulfide concentrations on uranium reduction as well. And so it likely reflects this whole range of ferruginous to sulfidic conditions. There have been some really nice compilations of uranium concentrations, uranium isotopes, and molybdenum concentrations and isotopes across some key intervals. I just want to highlight this nice one here, looking at redox proxies from the cryogenic to early Cambrian. And these authors interpreted these changes as reflecting changes of ferruginous or suboxic conditions versus euxinic conditions over this interval, and combine the interpretations together to tell a nice story here. And then just to plug a chapter that's coming out later this year, and if you want a copy, please email me, I can send you the PDF. But if we combine the uranium isotope proxy with a whole range of other redox proxies, then we can also tell a really interesting story of changing redox conditions through Earth history. So this is a compilation of sulfur mass isotope fractionation, sulfur isotopes in carbonates as well as in pyrite, shale, and carbonate delta-230 uranium, chromium isotopes, trace elements that are redox sensitive, such as rhenium, vanadium, molybdenum, uranium, as well as more carbonate-based proxies, the cerium anomaly, and iodine-calcium ratios through time. And what we can see is that where there are significant changes in these different proxies, actually record the evolution of redox conditions on Earth's surface very nicely, where we see change points occurring around the GOE in some key proxies here that likely reflect changes in atmospheric oxygen concentrations through time. And so here we can see that shale delta-238 uranium proxy occurring, reflecting changes in oxidation of the atmosphere. But then this later oxidation of the atmosphere in the oceans is reflected by this gradual evolution of different proxies. And I just want to highlight here, the uranium proxies seem to show a significant change actually early in the Phanerozoic that might indicate the oxidation of the deeper ocean compared to shallow ocean oxygenation. So I want to just leave you here with some future further resources. There are several recent proxy reviews or compilations that might be of interest if you're interested in learning more about uranium isotopes and the different complexities that this recent work has proposed in terms of how we interpret these proxies and how can we understand what they actually mean in terms of oxygen through time. Thank you.
Thank you so much, Kim. That was really great. I really learned so much, and I can't wait to see that chapter. That looked really cool. So now is our chance to really learn from Kim. So we get to turn off the recording and get to ask questions in an informal setting. So I'll turn off that recording now.